Now we have two important definitions. The first is a function on a manifold, and then we will define the tangent vector at each point of the manifold, and we will see that this tangent vector form a vector space and why. So first of all, if I have a manifold and a point of this manifold, I can find a neighborhood of this manifold, open set around it, as small as you like, or as big. It's not a problem. And if I can say there is function on the manifold, if there is function f that associate or that define a rule that assign each point of the manifold, assign it with a real number, so real valued function. Take a point at each point of the manifold, there is real valued. Real valued, that means there is value of Rn, the same degree of the manifold. This is the function. This is, I can define a function on a manifold in this way. And if it is mapped, each point of the manifold, there is real valued. If it is differentiable way, so I can call it differentiable function. F is a differentiable function on Rn. For simplicity, we can say it is Fb, but actually, more precisely, it's not Fb. It's f of the coordinate associated with this point, which are in our day. So this is very important things to have. But for simplicity, from now on we call it just Fb. That means this function defined at the point P. It's defined actually on the coordinate system associated with this, or coordinate set xi, which are associated with this point, and it gives a real value number, real value. And since the coordinates themselves are infinitely continuous and differentiable, and this should be clear in your mind. The second important definition is the vector, tangent vector. If I have a manifold and I have a curve, and we already defined what curve is, and we should talk about it fast in few words. Curve, there is a rule that associated, or a curve is a set of continuous point of manifold, that at each point of this manifold there is real valued in R1. So this is what we can call it as a curve. And now we need to prepare something. We need to define the vector field, the tangent vector. So I need manifold, I need curve, and I need function on the manifold. So function by definition is defined at each point of the manifold. And the curve, by definition, is a continuous series of points of the manifold. As a result, naturally, we can say clearly that there is a function f g lambda, which equal to f b at each point of p of the curve, because the curve is also each point of the curve is also a point of the manifold, and the function is defined on all the manifolds. So we can clearly and assure that there is such function j lambda. And since by definition that the curve is one parameter, one has just one parameter, and this property is very important. We will see later. And by this, since it is just one parameter, there is some of important consequence associated with this property. So let's make the derivation. Differentiate and use chain rule. of this function J lambda. Since it's unique, it's just one variable, I can say dg over d lambda equal dxi over d lambda df over dxi, and here I use Einstein convention of summing over the repeated index. You can not use it. You can just put sum, but that doesn't change anything. Which is also true. This is true with any J lambda. This is true for any J lambda. So we can write it in this way in the red box. And here we suddenly found the component of the tangent vector in green, and these are naturally the component of tangent vector dxi over d lambda. So it is tangent vector. So there is tangent vector at each point of the curve, and it is unique at each point. Unique. Why? Because it is the curve is just one parameter, has just one parameter. So only one tangent vector exists at each point of this curve. But here, this is true, but the opposite direction is not true. If I have a vector, there is infinite number of curves that could be tangent, that this vector can be tangent of them at this point P for several reasons. Because I can just change the rule of parameterization of any curve in a way that they tangent each other at this point P, but I don't care about what happened otherwise. So this is another properties. The most important properties now, and the final one, is this tangent vector form vector space. I can take, for example, linear combination a d over d lambda plus b d over d mu, which is by definition will be this sum multiplied by d over dxi, and this in black, they are this component in black box, surrounded by black box, are certainly a tangent vector of some curve at P. So the closure properties are satisfied. The other axioms are trivial. So the tangent vector form tangent space on the manifold.